All right, so today we continue with unitary and orthogonal operators. So last time we have stated a theorem which gives us several equivalent characterizations for when a linear operator is an isometry, right? So let me recall the statement of the theorem. So this was theorem 618. Okay. Assume that T is a linear operator on V, where V is an inner product space, and the dimension of V, as usual, is finite. Okay. Then we have the following equivalent conditions. So all of which are equivalent to each other. Yeah. So we have the first A, the composition of T with its adjoint is equal to the composition in the opposite order, is equal to the identity operator on V. So we have B, that the inner product of T of X and T of Y is equal to the inner product of X, Y for all X, Y in V. Okay. And we have further conditions C, D, and E. But I think I will start proving the implications one by one after stating the corresponding properties. Okay. So I'm going to write a proof on the next page. So first we're going to prove that A implies B. Okay. So we'll do it as usual. When you have a bunch of equivalent conditions, it's enough to find one sequence of implications which closes the loop, right? So we'll show that A implies B, B implies C, etc., all the way down to E implies A. All right, so let's prove first that A implies B. So A tells us that the composition of T with the adjoint in any order is just the identity, right? So it does nothing to a vector. So let's use this. So let's fix a pair of vectors, x, y, and v. And we try to compare the inner product of x and y with the inner product of t of x and t of y, right? So we have the inner product of x and y, okay? Now, by A, we're assuming that the composition of T with its adjoint is just the identity operator, right? So this tells us that we can write in particular T star composition T applied to the vector X inner product with Y, okay? Because we know that this linear operator is equal to the identity by the assumption A. Okay, so it's just the same as the inner product of X and Y. Okay, but now we can use the definition of the adjoint. So this is the same as the inner product of T of X and the adjoint of the adjoint of Y, right? So if this is just by the definition of the adjoint of T star. Okay, so we're using the usual formula for adjoints applied to the linear operator T star. Okay, so we get this, but now look, we are taking the adjoint of the adjoint, right? And we know that this is just T itself. So the adjoint of T is just T. So this is the same as the inner product of T of X, inner product of with T of Y. Okay. And what I just mentioned, that this is just T itself, this was theorem 611D. Okay, so this sequence of equalities shows that X inner product with Y is equal to the inner product of T of X and T of Y. So this shows that B holds, right? So we have shown that A implies B. Okay, now let's do the next equivalent property, C. So we have that if beta is an orthonormal basis for V, then T of beta is an orthonormal basis for V as well. Yeah. So applying the linear operator to each vector in a basis, in an orthonormal basis, we still get an orthonormal basis as a result. So this is property C. Okay, so now let's show that B implies C. Okay, so we assume we are given a basis, beta. Let's say it consists of the vectors V1 through Vn. Okay, so let this be an orthonormal basis for V. Okay, so we want to calculate T of beta. Well, not calculate, but to understand T of beta, where we have, by definition, this is just the vectors T of V1, T of V2, etc., all the way to T of Vn, right? Okay, so we want to show that this is still an orthonormal basis. So by assumption, we know that the inner product of Vi, Vj is equal to delta Ij. Okay, so recall this simply means that it is equal to 1 if I equals j and equal to 0 if I is not equal to j, right? So we just use this symbol. So we have this because we're assuming that beta is orthogonal in particular, right? So all the inner products of any two distinct vectors are 0. And because it's orthonormal, the inner product of any vector with itself is 1. This is just the square of the norm. And each Vi is a unit vector, right? So we have this, okay? But then we can apply B. So by property B, which we're assuming, we then have also the same property for T of Vi, T of Vj, right? So we have T of Vi, T of Vj is also equal to delta Ij. Because B literally says it's the same value as the inner product of Vi with Vj, right? Okay, but this looks promising, right? Because now we have to argue that T of beta is an orthonormal basis. So we have that if we look at the square of the norm of the vector Tvi, okay, square, then we get that this is the same by definition as the inner product of T of Vi with itself, so with T of Vi. Okay, now by B, this is the same as Vi inner product with Vi, which is the square of the norm of the vector Vi, which is just 1, because Vi, all of the Vi's were unit vectors. Okay, so the conclusion is that we have all Tvi are unit vectors, right? And they're all orthogonal because we have this. So, and orthogonal to each other. Well, let me say more precisely, and the set T of beta is orthogonal. Hence, it is an orthonormal basis. Okay, so why is it again a basis? Because we know that because we know that the vectors V1 through Vn were a basis, right? And so we know that if a set is orthogonal, then it is linearly independent. So T of beta is a linearly independent set of the same cardinality as the dimension of the space, right? Which was n. So it is a basis in particular. Okay, there's a question in the chat. Isn't this inner product being Dij enough to say it's an orthonormal basis? Yes, it is enough. But so that's what I explained it. Yeah. So you need to check it, and that's what we did. But that is a sufficient property. Yes. Okay. All right, so we have this, right? Now let's look at the next equivalent condition. So we have D. Oops, let me switch to the same color. So we have D. D is a property which says that there exists an orthonormal basis beta for V, such that we have that T of beta is also an orthonormal basis for V. Okay, so note the difference with C. In C, we say that this property holds for every orthonormal basis for V. But here we're just saying that this holds for some orthonormal basis for V. Yeah, so in view of this, it's obvious that that C implies D, right? So C implies D is obvious because we know that by B, sorry, not by B, by C, we know that D holds for every orthonormal basis. Right? And we know that it exists because the space is finite dimensional. So there exists an orthonormal basis. So just pick any that you like. And then C guarantees you that it's going to satisfy this property. Hence D holds, right? Because we found some for which we have this property. Okay, so the implication C implies D is straightforward. Just because, yeah, D is a weaker property at the face of it. But a posteriori, we see that it is actually equivalent. Okay, and the last one, we have that T is an isometry. So we have that T of X, the norm of T of X is equal to the norm of X for all X and V. So that is T is an isometry in the sense of the definition we made earlier, right? Because isometry just means a linear operator which preserves distances or norms of all vectors. Okay, so let's show that D implies E. Okay, so take a vector X and V and take a basis beta. Let's say V1 through Vn. And that's a normal basis. Okay. Then we have that we can write X as a linear combination of vectors and the basis, of course, right? So we can write this is equal to the sum over I from 1 to n, AI Vi for some scalars AI in F. Okay. So we have this. Now let's calculate the norm. So let's look at the norm of X, and we take square, not to have to keep track of the square root all the time. Yeah. Let's just plug this expression for X, the linear combination. So we have this as the inner product of the sum of AI Vi with itself. So the sum AI times Vi. Okay, we have this inner product. Now we can use linearity or bilinearity, or sometimes this is called sesquilinearity because we have to take the complex conjugate, whichever word you prefer, yeah. But we just use this property that the sum and the scalar, we can take it out of the inner product. So here we have to do it many times, but in the end we get that we have the sum I from 1 to n, the sum overall j from 1 to n, and here we have AI times the complex conjugate aj times the inner product Vi Vj. Okay, so this we get just using the properties of the inner product. That is linear in the first coordinate and well, for the second coordinate, you have to take the complex conjugate, right? So doing this inductively, we get this, okay? But now we can use that beta is orthogonal. So beta is an orthonormal set, an orthonormal basis. So this tells us that a lot of these inner products become zeros, right? So let's write out the ones which don't. So if you think about it for a minute, we see that we get the sum over all I from 1 to n, the sum over all j from 1 to n, and we have ai complex conjugate aj times delta ij, right? Well, this is just by definition of orthogonality, or orthonormality, sorry. And now delta ij, of course, is 1 when I is equal to j and 0 otherwise, right? So this means that we are just left with the sum over all I from 1 to n, ai times aj complex conjugate, right? Everything else becomes 0. Question in the chat. Should we change the first summation as j as well? No, look, because it's important that there are two indices, right? Because we have here we have two sums, right? So to calculate this inner product, I have to first take first element here, then take the inner product with the first element here, then I take still first element here and take the product with the second element here, etc. So this means I have to take the sum over all pairs ij.
So the second summation in the first inner product, I meant, we change it from...
Here it doesn't matter, yeah, look, because here the index doesn't matter because each sum is just uses one of the indices at a time, right? So here we could write j instead if you prefer here. It doesn't change anything, right? But the whole point, the important point though, that when you have a sum which involves two indices, when the summand depends on two indices, then we have to be careful that they actually vary separately, right?
Thank you.
Okay, sure. Yes, okay. And so the result, we have this sum here, right? And what is this? So this is the same as the sum over all I from 1 to n, the absolute value of ai square, right? Because ai times ai complex conjugate is just the absolute value of ai squared. Okay, so this gives us the expression for the square of the norm of x. So now we want to do the same, but for the norm of t of x. Okay, so applying the same calculation. To the vector t of x, which is just the sum over all I from 1 to n, ai t of vi, right? And using that t of beta is also an orthonormal basis. Right? And this we have by d. So maybe I didn't stress it here, right? Here, when we start with beta, it's not an arbitrary orthonormal basis. I should have said it's a basis given by d. Okay, so very important. Given by d. So it's an orthonormal basis, so that t of beta is also an orthonormal basis. Okay. So we are using this now. Okay, so we can do the same calculation. So I'm not going to write it fully, but it's exactly the same as we did for x, but now you just do it for the norm of t of x squared, okay? So you can just use the same thing as we did. Use that t of x is given by this sum, take the inner product of this sum with itself, etc., and continue. And since t of beta is an orthonormal basis, we get that the square of the norm is, so a lot of things cancel out again, become zeros. So we are left with the same thing, the absolute value of ai square. Okay, so I encourage you to check it yourself carefully. And the point then we proved that the two are equal, right? So we have that t of x norm square is equal to the norm of x square. So, and both are non-negative, right? The norm is always non-negative. So we get that this means that the norm of t of x is equal to the norm of x. and x was an arbitrary vector. Let me, oh, that's my mistake, I think. It shouldn't be j, it should be I, sorry. Here it should be the same I. First of all, this is a typo. Corrected, but let's see. So I look at the sum. So it's a double sum, right? So it means I have to fix I, and then I have to sum overall j, what remains here. So now if I fix any I, then and I now let j range between 1 and n. So I get that for every j which is different from this fixed I get 0 here, right? So then the whole sum, this one, for a fixed I becomes just AI times AI complex conjugate. So this was, yeah, this is what I should have said here, AI. And then this just becomes the sum like this. Okay, yeah, thanks for pointing this. All right, so we proved D. So to finish, we need to prove to close the circle of implications, right? So it remains to show that E implies A. Then we will know that all of these properties are equivalent. Okay. All right, so let's do it. So again, let me go back for a second, just to remind you the properties. So A tells us that the composition of T and its adjoint is the identity. Yeah. And E says this is an isometry. Okay. So fix any x in V. Then for any x in V, we have that the inner product of x with itself is the same thing as the square of the norm of x, right? Now, using property E, well, we're assuming E. So using E, we get that this is the same as the square of the norm of T of x, right? Which is by definition the same as the inner product of T of x with itself, right? And now by the definition of adjoint of T, we get that this is the same as the inner product of x. And now I have to apply T star to the vector T of x, right? But this is just the same thing as T star T of x. Okay, so we get this. So we have the equality of the inner product of x with itself and x with T star T of x. So we get that the inner product of x with the identity operator I minus T star T of x is equal to 0. Yeah, so this holds for all x and V. Right? So we get this. Now, let us take U to be this linear operator, I minus T star T. Okay, so let's look at this linear operator. First of all, we note that U is self-adjoint. Okay, so let's check this. Why is this true? Because we have that the adjoint of U is equal to the adjoint of, well, I just take the definition for U. So I have I minus T star T star, right? And now we use the properties of the adjoint operator for from theorem 611. Okay, so I'm going to use theorem 611 here and throughout all these equalities. So this is the same as I star minus T star T star, right? Because the adjoint of the difference of two operators is the difference of the adjoints. But the adjoint of the identity operator is just the identity operator itself. So we get I minus, okay? And here we have to take the adjoint of this. So this gives us T star, T star star. So I'm using again theorem 611 for all of these equalities, right? 611. Okay, but since we have this, so what is this? This is the same as I minus T star T, right? Because the double adjoint of T is just T itself. and we get u again, right? So we just obtain the expression for u again. Okay, so this shows that the adjoint of u is u itself. So u is self-adjoint, all right? And we also have that the inner product of x with u of x is equal to 0 for all x in v, right? So this we just observed earlier. Okay, so look, so now we have a self-adjoint operator, u, so that the inner product of x with ux is equal to 0 for all x in v. So now I'm going to use the lemma that we proved at the end of the previous lecture. So by the lemma, at the end of the previous lecture, we get that in this case, T0 is equal to U, right? So any self-adjoint operator with this property is going to be the 0 linear operator. And again, this is I minus T star T. Okay. So since we get that this is the 0 linear operator, it follows that T star T is just the identity operator, right? The sum is 0, so they're equal. Not the sum, sorry, the difference is 0, so they're equal. Okay. All right, so we get this. Okay, so this is half of what we needed for A, because this tells us that if we take T star T composition in this order, we get the identity. Now we have to argue that we get the identity in the opposite direction as well. If we compose in the opposite direction, T star as well, right? Okay, so for this, recall from 115a, so it's a fact from 115a about matrices, that given two square matrices, AB, let's say, n by n matrices over some field F, if we have that the product AB is equal to I, yeah, so the product in one order of these two matrices is the identity matrix, can write IN to be precise, then we also have that BA is equal to I as well, right? So, okay, so now we can use it to get what we want for the operator if you look at the matrices representing it. Okay, the usual trick. So we have for beta any orthonormal basis for V, right? We get that the T star T, the composition, is the identity, implies that the matrices representing them, so the matrix representing T star with respect to B, times the matrix representing T with respect to B, is equal to the identity matrix, right? But by what we just said about matrices, this implies that the product in the opposite order, so first the matrix representing T, then the matrix representing T star is the identity matrix, okay? Which of course implies, since matrix multiplication corresponds to the composition, this implies that T star is equal to I, okay? And so we have proved that T star T equals I and that T star equals I. So we have proved A holds. And this concludes the proof of the theorem. Let me see. Why does beta need to be orthonormal here? Maybe it doesn't. Yeah, okay. I thought maybe we would need it if we take the conjugate out of the the adjoint out of the matrix, but we actually didn't even need it here. So I guess beta could be any basis in this argument, but it doesn't harm to take an orthonormal one, right? Doesn't harm. Okay. Oh, and there's another question. So can we use that T adjoint of x square equal the norm of T of x square equal x square? But let me see. But do we know it? Can we assume it? So we have T. Did we prove something like this? Maybe I'm forgetting. So there definitely could be different arguments. Yeah. So maybe email me if you want to discuss it. Okay. Yeah. Yeah, I think, I mean, we probably could use something like this, but I need to make sure that we actually have verified all of this property. Okay. So anyway, let me pause for a second if there are any other questions. Okay, so we have this, oh, why did we care that U is self-adjoint? Because in the lemma, this was needed. So for the lemma to be true, the lemma from the previous lecture, it was needed that U is self-adjoint to get the conclusion that then it is at the zero operator. If you look back at the proof of the lemma, yeah, it uses it. Okay. All right, so we have this theorem. Now let's record some corollaries of this theorem. So it has some useful corollaries. Okay. So the first corollary, corollary 1, we have that if T is a linear operator on V, where V is a real inner product space, okay. So in this corollary, we restrict to real inner product spaces of finite dimension. Then we have that V has an orthonormal basis of eigenvectors of T with the corresponding eigenvalues of absolute value 1. Okay, so we have this additional property now that all eigenvalues have the absolute value 1. This happens if and only if T is both self-adjoint and orthogonal. Okay, so we have this characterization in the same pattern as we had previously for self-adjoint. So remember, self-adjoint for a real inner product space, self-adjoint is equivalent to having an orthonormal basis consisting of eigenvectors, right? So now we introduce this additional condition, which will characterize when it is moreover orthogonal. And the corresponding condition is that all the eigenvalues for the eigenvectors in this basis have absolute value 1. So yeah. So they can be -1, 1. The absolute value is 1. Okay. Let's prove this. So first we show the implication from left to right. So suppose we have such an orthonormal basis. So suppose V has an orthonormal basis beta given by V1 through Vn such that we have that T of Vi is equal to lambda I Vi, and all these eigenvalues have absolute value 1, right? So lambda I, the absolute value is equal to 1 for all I. Okay, so this is what the left-hand side says. So assume we have it. So let's show that, well, first of all, we know that T is self-adjoint already, right? Because by theorem that we proved earlier, this was theorem 617, we know that T is self-adjoint. So this part doesn't use anything about the absolute values of the eigenvectors, just that there exists an orthonormal basis. Okay, of eigenvectors, sorry. Okay, so it is self-adjoint. So what we need to prove additionally is that it is also orthogonal. So in other words, that it is also in isometry. For this, we could use any of the equivalent characterizations that we just proved, right, from the list. So the one which is the easiest probably to use here is in terms of the composition with the adjoint. So we have that T star, the composition in this order, evaluated on the vector Vi in the basis. So by definition, this is the same as just applying T to the vector obtained by applying T star to Vi. This is just the definition of the composition, right? Now, this is the same as T of Vi using self-adjointness, right? Because it's self-adjoint. So we can replace T star by T. Now, this is the same as T lambda I Vi, right? Because we have that T of Vi is equal to lambda I Vi. Now, just use linearity. So this is equal to lambda I T of Vi, right? Because T is linear. But this is, again, what is T of Vi? We know that T of Vi is this, right? So this is just lambda I times lambda I times Vi. Okay, we get this. So this is the same as lambda I square times Vi. And we have this for each I, for each vector in the basis. Okay. So, oh, and I didn't finish, I guess, right? Because, okay, here is where we use the assumption. So remember, the absolute value of lambda I is 1, right? So in fact, that's why we get that this is equal to just Vi. Because lambda, the absolute value of lambda I is 1, so the square is also 1. So we get that this is equal to Vi. And so the conclusion is that T star is the identity operator. Because for any vector Vi in the basis, it doesn't do anything, it just gives you the same vector Vi in the basis. But then by linearity, if it doesn't do anything, if it doesn't change the vectors in the basis, then on the whole space, it's also the identity, right? So we get that this is equal to the identity. When we take the composition in this direction, right? Okay. But then also, as in the end of the previous proof, we get that if we take the composition in the opposite order, we still get the identity. Okay. And so the point is that then it follows that T is orthogonal by theorem 618A, right? So this was the condition A in one of the equivalent conditions for being an isometry. And remember, orthogonal just means isometry when we are working in a real inner product space. So this proves the implication from left to right. So now let's prove the opposite implication. Yeah. Because we want to show this is an equivalence. So assume that T is self-adjoint. Okay. Well, it's part of the assumption. Then again, by theorem 617, we know that V has an orthonormal basis, beta. We can write it as V1 through Vn, such that each vector in this basis is an eigenvector. So TVI is equal to lambda Vi, lambda I Vi, for some lambda I in F, excuse me, right? Okay, so we have this. Now we use that T is also orthogonal. So as T is also orthogonal, we can use that it preserves the norms, right? So we have that the absolute value of lambda I times the norm Vi is the same as the norm of lambda I Vi And this is the same as the norm of T of VI. And this is the same as the norm of VI, right? So this is the place where we use orthogonality. This one here, right? The other ones are just basic properties of the norm. Okay. So look, we have that some scalar, the norm of VI is equal to the norm of VI, the same scalar, times some the absolute value of lambda I. But this is only possible if the absolute value of lambda I is itself equal to 1, right? So we have that this is equal to 1 for all I, which is precisely the left-hand side of the in the statement in the corollary. So this concludes the proof of corollary 1. Okay. Let me pause for a second if there are any questions. Okay, if not, we also have another corollary. So corollary 2. Assume this time that T is so almost the same situation, but with a small difference. So assume T is a linear operator. For V, a complex inner product space. So in the previous case, we had a real inner product space. Now we have a complex inner product space with dimension of V finite. Then we have a similar equivalence, but there's a small difference. So it gets easier actually. So now we have that V has an orthogonal, orthonormal in fact, not just orthogonal. Sorry, as usual, yeah, orthonormal basis of eigenvectors for T with corresponding eigenvalues of absolute value 1. Okay, so the same exact statement as we had before. And this holds if and only if, but now the condition is easier. If and only if T is unitary. Okay. So here we don't have to impose any additional conditions. So just enough to say that T is unitary, as opposed to self-adjoint, the additional self-adjoint requirements like we had here. Okay. And I think this should make sense because if you remember, if you ignore the absolute values part of the condition, for the existence of the orthonormal basis, all we needed in the complex case was normality, right? We didn't need the additional condition of self-adjointness. So here, so here the condition, then the second condition is easier, just that T is unitary. So T preserves the norm. And the proof of this is actually part of the homework. So proof, it is similar to the proof of corollary 1. So see homework. Just the point, one point is that the difference now, we don't use the result for real inner product spaces, which characterizes when we have an orthonormal basis of eigenvectors, right? We use the analogous theorem that we have for complex inner product spaces that characterizes this property. Okay, so that's the main difference here. Okay, so these are two corollaries. Let's consider also an example. Okay, example. Some concrete, what happens in some concrete, for some concrete linear operator that we already saw, namely the rotation. Okay, so assume that T is a linear operator on R square defined by rotation. So this is a rotation by angle theta for some theta strictly between 0 and pi. Okay. Then T preserves the length of all vectors right? Because we are just rotating them. So let me draw a picture maybe also. Okay, so the rotation operator. So if I have a vector x and I apply t to it, what I get is the vector t of x. So it's obtained by rotating by angle theta. Yeah. And the length of the vector doesn't change. We just rotate it. Okay, so the length doesn't change. And hence, it also preserves the standard inner product on R square. This is by theorem 618, right? So what do I mean by preserves? Let me maybe define it precisely. So preserves, by this we mean that the inner product of xy is equal to the inner product of t of x, t of y for all xy in V, right? Because if it preserves the norms of all vectors, then by the theorem we just proved, it also preserves the inner products of any pair of vectors. Okay, but then for beta standard basis of R2, we know that the matrix representing the rotation operator, so again, we already discussed this example, is given by this expression. Okay, so this is the rotation matrix. Now, what we get, if you try to calculate this, okay, we can check that T beta is not equal to the adjoint of this matrix, to the complex conjugate of this matrix. Yeah. If you just look at, well, just rotate the matrix and you can see that you can't get an equality here. Okay, so it's not self-adjoint. So T is not self-adjoint. So the rotation operator is not self-adjoint in general. Okay, and so it also follows from theorem 615 that because there are no eigenvectors. Okay, so this conclusion that we can obtain from this direct calculation also follows because there are no eigenvectors, right? And if it was self-adjoint, we would have a basis consisting of orthonormal basis consisting of eigenvectors. And we know there are no eigenvectors because, again, something we already discussed, right? Because every vector gets rotated because 0 is strictly greater, well, it's strictly between 0 and pi. So every vector does get moved a little bit, rotated. So it's not just multiple by some scalar of the vector you start with. Okay. And here, if you convert if you look at this matrix and try to calculate the complex conjugate, what we get in this example is that the adjoint of the rotation operator is the rotation by the opposite angle. So T star is the rotation by minus theta. Okay, so in this case of rotations, we have this very geometric meaning of interpretation of the adjoint operator. So if T corresponds to translating by theta, then the adjoint corresponds to, sorry, not translating, rotating. Then T star corresponds to rotating by minus theta in the opposite direction. Yeah. Okay, so we have this nice example. So we have rotations which are normal operators, but not self-adjoint. Okay. We want to understand some other kinds of geometric intuitions behind some other normal operators. So we'll see some more examples next time. We'll talk about reflections, for example, and eventually we'll obtain a classification of all orthogonal operators in some nice inner product spaces. Okay, but this is just a small teaser for the future. So the idea is to get some nice geometric intuitions in some of these important special cases for all these abstract operations that we have and theorems that we have been developing. But let me stop here. So I'll stop here today, and yeah, and we'll discuss reflections and other further properties and matrices of all such operators, etc. Starting next lecture. Okay. Yeah. All right. Yeah. So thanks everyone. I'll stop here. Yeah. Thank you.